If you are new here, Nipah is a fruit bat virus that can spread to humans. In this video, we are focusing on what would need to change for it to spread through the air. Nipah is terrifying because it can kill up to 75% of people in some outbreaks. But outbreaks usually burn hot and then fade because Nipah has a limitation. It does not spread easily through the air like measles or like COVID did. Now imagine it changes. Not one small mutation, but a real shift in how it survives, exits the body, and enters the next person. Today, I am breaking down what would actually need to happen at the molecular level for that to be possible. But here's what most headlines get wrong. Airborne transmission isn't about mutating more. It's about mutating smarter. And that difference could mean everything. Nipah virus lives quietly inside fruit bats of the genus Pteropus. In bats, it's stable. It doesn't make them sick. In humans, it can trigger brain inflammation, respiratory failure, seizures, coma. Outbreaks are usually explosive but limited because Nipah spreads mainly through close contact, bodily fluids, and contaminated food. They don't spread through the air yet, and that limitation changes everything. But what if the very tissues Nipah prefers are the reason it can't spread through the air? Nipah targets deep tissues. It binds to receptors called ephrin B2 and ephrin B3, abundant in brain cells, blood vessel linings, and deep lung tissue. That's why it causes encephalitis. But airborne viruses follow a different strategy. For instance, measles virus replicates aggressively in the nose and throat. That's key. Airborne transmission requires massive viral replication in the upper respiratory tract, shedding before severe symptoms, easy release through breathing and talking. For Nipah to change, it would likely need mutations in its G-glycoprotein, which is the surface protein that determines which cells it can enter. That is rewriting its biological targeting system. But even if Nipah learned to infect the nose, it still wouldn't be airborne because surviving outside the body is an entirely different battle. Picture a microscopic droplet floating in dry air. When the UV radiation hits it, humidity drops and the droplet shrinks. Inside it, a viral particle struggles to survive. Nipah is an enveloped virus. That means it has a fragile lipid membrane or a fatty outer layer. That membrane is vulnerable. Compare that to highly airborne viruses like SARS-CoV-2, which evolved features that increase environmental stability. For Nipah to spread through the air, mutations might need to stabilize its envelope proteins, reinforce matrix protein structure, improve particle integrity in tiny aerosols. That's a second major evolutionary hurdle. But here's the twist most people don't expect. If Nipah ever became airborne, it might actually become less deadly. Currently, Nipah is often severe, quickly. Many patients deteriorate within days. But evolution rewards transmission, not destruction. Airborne viruses usually spread before the host becomes incapacitated. So, if Nipah evolved for respiratory spread, natural selection might favor milder early symptoms, longer infectious windows, and delayed neurological damage. Paradoxically, greater spread could mean lowercase fatality rates. Evolution often trades lethality for reach. It's the way to continue living. So, the real question is, how many mutations would Nipah need to align at once? To become efficiently airborne, Nipah would likely need 5 major changes in its structure, such as enhanced replication in nasal epithelial cells, modified receptor affinity in upper airways, greater aerosol stability, reduced immediate lethality, and sustained human-to-human transmission chains. That's not only one mutation, that's a coordinated cascade, and that matters because right now, outbreaks are sporadic, limiting transmission and consequently limiting evolutionary opportunity. Without long human transmission chains, adaptation slows, but evolution accelerates under pressure. So, what would increase the odds? Major risk accelerators would include larger, sustained outbreaks, dense urban transmission, increased spillover frequency, and delayed outbreak detection. More replication equals more mutation chances. However, current data shows there is no evidence Nipah is trending toward airborne adaptation. Its genome sequencing hasn't revealed coordinated respiratory adaptation patterns, and that's critical. So, are we one mutation away? No. And here's why that phrase is misleading. Becoming airborne is not a switch, it's a systems-level transformation. Viruses are constrained by structural protein compatibility, receptor distribution, immune system pressures, transmission dynamics. Organizations like the World Health Organization and the Centers for Disease Control and Prevention monitor outbreaks precisely to detect multi-step shifts early. So, could Nipah evolve airborne transmission? Biologically speaking, yes. However, no evidence supports that it would occur imminently. It would require tissue retargeting, structural stabilization, evolutionary trade-offs, and sustained selection pressure. That's a tall barrier. The real danger is misunderstanding how evolution actually works.